Okay, let's get started. I have a bad sore throat, so hopefully you can still hear what I'm saying. So I got the email about the collaboration stuff, right? So in general, be more conservative. If you ever worked with somebody on any of the projects, let me know. I'm not going to take any points for collaborating with people, but if you don't say that, then I assume that there's something going on. So especially you see stuff like one person says they work with 4 people, and other 4 people don't say they worked with him, so that's kind of like a bad sign, right? So today we're supposed to continue with the notion of virtual memory, right? So are there any questions about what we covered so far? Especially with segmentation and with paging, right? So virtual memory we sort of talked about it, even though we didn't talk about it formally before. The idea here is there is no reason why, we never talked about what's the relationship between logical address and physical address, right? The assumption was, you have to have a page table of some size, right? And that size depends on how you want the system to be organized. So far we kind of assumed that they were related to the physical memory size, but there's no reason why it should be. And the notion of virtual memory essentially says that you can make the logical address space larger than physical address space, right? Which means that if you have a machine with, say, 2 gigs of memory, and if you're on a 32-bit machine, so your logical address space would be 32-bit, which is 4 gigabyte, whereas your physical address space is only 2 gigabyte, right? And that's the notion of virtual memory. And once you do that, you're able to do a lot of other nice tricks, and that's what we're going to cover in this chapter, right? And many other things don't change. I mean, we still use the same techniques that we learned so far, and some of them we tweak a little bit, right? So in this notion, you want the logical address space to be bigger than physical address space. Is there a reason why you want to do the other way, where the physical address space is larger than the logical address space? So here we are assuming that logical is bigger than the physical, right? So you can access address which is directly not mappable to the physical memory. But can you think of reason why you may consider the other way, where the logical address space is smaller than the physical address space? Does it make sense at all? Yeah.
Maybe like virtual machine.
We're not going to cover virtual machines. No, virtual machines don't do that, right? They still. It's an orthogonal issue, so they don't do this stuff. But you are right. That's one of the reasons why you might want to do that, right? Virtual machine has some reason where you have a larger physical memory. You have multiple machines running on the same stuff, and they can access the stuff, right? It made sense when you had the logical address space as 16-bit or 8-bit or what have you. If you have embedded processors, or if you're talking about older machines, which were 8 or 16-bit, then it's possible that 16-bit is really 64K. So it's possible to have more memory than physical memory, right? But the modern processors are, so if you consider 64-bit processor, the logical address space is 64-bit, which is a very big number, right? We're not going to have more physical memory than that anytime soon, right? So it's not that often where you see something like that, right? So the idea here is you have the logical address space is more than physical memory. That means you need to play games on making sure the application, it looks like you have the logical address space, right? That means you may have to move the pages back and forth. You may have to swap pages back and forth to hard disk, such that it looks like you have the logical address space available to your program, right? And having this facility helps you in other ways, right? One of the things I talked about in the last lecture was when you have different segments, right? If you keep them too close to each other, right, then it's not possible for them to grow, right? So if you have the hash and the text segments right next to each other in the logical address space, so if they want to grow, if the text segment wants to become larger, then if they're close together, then you're kind of bounded by that, right? Remember, this is what we're talking about. So eventually everything gets mapped to a logical address space, right? So if you had, let's say, text segment here and the data segment here in the logical address space, if this distance was close by, right, then the text can only grow up to this much, right? If you want your program to add more text, it can only grow up to this point. And if you had something else here, the data segment can only grow up to this much, right? With this notion, since you have the whole logical address space in your stuff, you can increase this space, right? Even on a machine which has, let's say, 64 meg of memory, you can put this and this pretty far out in the logical address space, in which gives you flexibility in the different segments growing, right? And that's one of the nice things about having a virtual memory. So the notion of how to move these things back and forth such that it looks like you have the whole logical address space, even though it's not there on the system, you can do that through demand paging or demand segmentation, right? Which is essentially the idea of the using the swap disk. So the idea here is if you have a page, right? You have a page you put it on the swap disk. You basically bring it in when you need it, and when you're done, you put it back, right? So that way, you can have a logical address space which is bigger than the physical address space. So now you're only bound by how big the swap space is, right? As long as the swap space is really big, you can move these things back and forth such that when you want it, it's brought to the main memory, and something which you don't really need is moved back to the swap disk. So if you do this in a good fashion, you may not notice much performance drop, which is what you're seeing in most of your machines, right? So there are some conditions we'll see where it's going to be annoying. You're going to see lots of page faults. But there are other conditions where you're not going to see lots of page faults, right? So that's the way you do that. Again, going back to what we talked about when the operating system gets involved and stuff, operating system does not get involved with every memory reference, right? So you want some mechanism to make sure that when you access a page, whether it's valid or invalid, and if it's not valid, then you need to do some things. And for that, you need hardware support, right? So we use the same notion of page table we had before, and we mark some pages as invalid or valid, and we use that to interact with the OS. So the idea here is for the different pages in the page table, you have this notion of an invalid or valid bit. Those are set by the operating system, right? It sets the validity bits on the page table. The hardware promises that if it was set invalid and you try to access that logical address space, then it'll give you a page fault, right? That's how they cooperate. So the operating system manages these fields, and the hardware will give you a page fault if it's not here. So for the pages which have 1, that means that those pages are valid, because that's sort of set by the operating system. That means those addresses will go through without involving the operating system. For these pages, those are invalid. So they may be invalid because of 2 reasons. One is you're accessing a page which you're not supposed to. You're accessing a logical address which wasn't allocated to you. Or you're allocating a page which was allocated to you, but it's in the swap disk, right? So depending on the case, you'll have to look in this another data structure to see whether it's a valid address which needs to be swapped in, or it's invalid address. If it's invalid address, you get the segmentation fault. If it's valid address, then you'll have to move the pages around. And so we have a illustration of how these things will work. So here, so you have the page table with the different validity bits set, right? And so essentially, in the logical address space, you have A, B, C, D up all the way to H, right? Only 3 of them are on the physical memory. The other ones are set to invalid, right? And it's up to the operating system to make sure that it's somewhere. In this case, it's going to be in a swap disk. We'll see what swap disks are in the next module. For now, assume that this is some area where you can store all this content, right? So essentially, if you try to access one of those frames, any of those logical address pages, if it's invalid, you get a page fault, and it's up to the operating system to decide what to do, right? So if you try to access something here, then it's not part of your process. So the operating system will give you a segmentation fault. But if you try to access, let's say this one, it knows that 7 has to be at SH, right? H has to be on the backing store, right? So you need to bring it back in from the backing store, right? So for all this to work, you need to have this notion of a page fault. Essentially, the hardware will tell you that something is not there, right? And so you need to have another data structure within the operating system which keeps track of what is valid, which is in the soft disk, and what is invalid, in which case you need to give a page fault, segmentation fault, right? So let's look at what all the steps that happen when you do get a page fault, right? So you follow the references from on the order of the numbers given. So essentially, you set up the operating system sets up this page table and gives control to the hardware, right? Your program starts to run. If your program accesses a page which is invalid, right, you get a page fault, and then you get a page stub to the operating system. It has to see what happens. It has to see whether this is because it's invalid entry or it's a valid entry. If it is for a valid entry, it has to go in the backing store. It has to find something free, which may mean that if it is free available, then you can store it here. If it's not freely available, you have to find something. You have to kick it off, move this page here, and once you're done, you update this entry, make that field valid, and you restart the instruction, right? So from your program perspective, you won't notice anything happen except things will be slow, right? Because hard disks are typically very slow, so you will notice timing issues. But from a program perspective, you won't know all this happened. Does that make sense? Right. So this is essentially sort of what you're trying to do for your homework project, right? You're trying to go through these steps and trying to see how many faults you will get for different programs. And the print tool is pretty nice. And print tool is something that you can use to see how your program behaves. Even in the case of a two-dimensional array, if you go row-wise or column-wise, you can see how it generates logical addresses and how one of them is good, one of them is bad, right? So the key here is to figure out what is the page replacement policy, right? By definition, your physical address space is smaller. That means you have to remove something, right? So when you want a new frame, if there is a free frame available, then you're good. Otherwise, you have to decide some things to kick out, and you develop some policies on figuring out which ones to kick out. So essentially, when I want a new frame, I need to throw something back to the hard disk, and then bring my new frame in. And there are several. You can think of what is the performance you expect, right? And it's a simple equation, So essentially, what happens is for a program, you figure out what's the page fault rate, right? So for a given page fault rate, this is the cost it takes for you to run your program, right? So for a page fault rate, let's say it's 0 to 1. 0 meaning there's no page fault. 1 being every instruction is a page fault, right? And obviously, you don't want to operate when every instruction is a page fault, because going to the hard disk is so slow that your program will hardly make any progress, right? You would like it to be as close as possible to 0, right? And the effective access time, right, would be 1 minus p, which is the page. So if you assume that each instruction takes 1 unit, right, in main memory, so 1 minus p is what will happen if you hit the page, if you hit the, if the entry is valid, right? Otherwise, you get a page fault. You have to add the cost of moving it to the hard disk. You have to add the cost of moving it back from the hard disk. And then you have to add the cost of starting over, right? So if you plug in numbers for these, essentially, the page fault rate decides how good a performance you can get, right? So where does this page fault rate come from? Is it something that the operating system has control over, or is it something that who's responsible for, ideally we would like the page fault rate to be 0, right? That means everything is in memory, so you don't have to go to the hard disk, you get to run all the time. But who's the culprit? Who's the one which makes it less than 0, I mean greater than 0? Yeah. Sorry. Yeah.
Your programs?
Yeah.
Depending on how to access memory?
Yes. It's basically the programs, right? It's the program. So the operating system does not really have too much control over it. Does it have any control at all? Can it do something to help you intuitively? Do you think that it can do something, or it is essentially out of its control? Page faults are going to be caused by your program, right? So the way you write your program, depending on what you do, you may get a lot of page faults or less page faults, right? But is there something the operating system can do which can make the situation worse, or yeah?
Speculative catching?
Yes, those are different solutions to address this, right? But essentially what you want to do is, we'll see in a little bit a notion of a working set, right? So if your program is going through a loop, the operating system can help you by giving you a certain amount of memory that will make your system go faster, right? It can't really help you if your program is written really horribly. But if you have some sort of a pattern, if you can figure out what the pattern is, it can do something like what he mentioned, like speculative caching or whatever. If you can sort of figure out that you're trying to, let's say, go through this big loop, and you're going to access pages, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 kind of thing, then it could potentially give you enough pages such that you won't come back often, right? So if you have a program which goes through pages 1, 2, 3, 4, another one goes through 1, 2, it'll be good if you can give the page which goes through 1, 2, 3, 4, all the 4 pages, and the one which you have 1, 2, all the pages it wants. And that's the challenge of this whole process, right? If it can learn some of this stuff, and it can, what we call a working set, then it can really help you a little bit, right? It can't help you all the case, because if you try to mess the operating system up by accessing the memory randomly, then none of this will work. But it could make some difference, right? And that's one of the things you notice between different versions of operating systems when you buy it from the store, right? Windows Vista to XP could potentially make these things different, such that you would get better performance, right? So what is the one parameter that you can think of which will make the operating system decide to give you more memory or less memory? So one of the cases I talked about, there's one process which needs 2 pages, another one which needs, let's say, 10 pages, right? It goes to 10 pages all the time, right? And if it can learn this, it can sort of give you better performance. But what is the trend that makes the operating system make such a decision? For example, Windows 2000 to Windows XP to Windows Vista, right? Windows 2000 came in, let's say, 2000, XP came in 2002, this came in 2008, right? Vista. What has changed along this time that would make you as operating system developer do stuff differently? I'm not talking about 64-bit architecture. I'm talking about, if you consider 32-bit architecture, what is the one thing which has been changing? Your processors are getting faster, right? What about your memory? What's been a trend in main memory over the years? Yeah, it's getting bigger, right? If it gets bigger, then that means the operating system can be a little bit more lenient, right? It knows that, I mean, sure, I don't know what the minimum memory requirements for Vista, right? They may state that you can run it on a 64 meg machine or something, right? But no human being should run Vista at 64 meg or 4 meg or whatever, right? Normal human beings should run it on machine which has 1 or 2 gigs or what have you, right? because the memory is getting cheaper enough that you're going to get more memory. That means they can make assumptions which you couldn't do it back in 2000, right? So they can take the same operating system, but now they can say it's highly likely that people are going to have lots of memory. So if they're going to have lots of memory, then they can afford to give you more memory than what it did way back when, right? So in the hope that giving you more memory would mean that your same program may have less page fault. And that's one of the trends you, as operating system developers, they kind of follow, right? If the amount of main memory keeps going up, then a lot of these things become a lot nicer. You don't have to be stingy. You don't have to be extremely careful on how much you give. You can kind of let people have some memory because you expect good performance, right? And then as we go along, you'll see one of the things that you notice, right? Some of you may have noticed this, right? So if you had a machine which has half a gig of memory, and let's say you go out and buy like a 4 gig, right? You will still have your available memory practically the same, right? Even though you buy lots of memory, nothing really changes, right? How many of you noticed that aspect? Like if you go from half a gig, the same machine, you take half a gig, you put 4 gig, and then the amount of free memory still stays about the same, right? And there are some companies which sell these software which is supposed to clean up the memory, right? You run this program, it cleans up all the memory, and then you have lots of free memory, right? How many of you seen those programs for memory sweep, right? What do you think of those? Are those a good idea? Or I think that those are awful idea, right? The operating system of the newer generations know that you have lots of memory. They want to use it in a fashion where hopefully you get better performance, right? It's no use to have memory which is free. You want to keep it as much as possible. You want to use it as much as possible, right? So anyway, so the page fault is created by a program, but the operating system can still do something by giving you enough pages that you don't get the page fault, right? And here is some numbers on how you may see the performance, right? So if you have a page fault rate of like, if the memory access is 1 microsecond and the page fault is 50% page fault rate, and your hard disk is very slow, right? It's about 15,000 compared to 1 microsecond for getting some things. So your program slows down considerably, right? You might have noticed this when you start your program, right? When you start your PowerPoint or something, initially you see lots of pages there's a lot of page fault. You can hear your disk going wild. It's getting all the pages to run this program, right? And one of the optimizations that systems do is when you exit out of PowerPoint, it does not actually return all the pages somewhere else. It just kind of keeps it in the background, even though the process is not running. So when you run it again, your next time PowerPoint can be much faster, right? But the first time when you start it, you're going to see the hard disk going really crazy, right? If you don't believe me, just go into your machine and start PowerPoint, Excel, and Word at the same time, right? And see what happens to your machine, right? Your whole machine practically frees up because it's basically bringing the pages back in. And while it's bringing, your PowerPoint cannot make progress, your Word cannot make progress, your Excel cannot make progress. But once you bring all the memory in, you're kind of good, right? Because once you're bringing in, during the process of bringing in, you're paying this much cost. But once it's in main memory, you're paying this small cost, right? And there are other tricks we can do with the virtual memory notion, right? The virtual memory notion, if I don't need something, I don't have to bring it back in. And we can play other tricks which are pretty nice, right? And two of them are copy and write and memory map files. I'm going to talk about copy and write here, memory map files later, right? So these are two tricks which are done to make your system do certain things nicer because you have the notion of virtual memory, right? So copy and write is essentially the idea that it's called a cow, right? Essentially, the observation is when you create a process, right? When you do a fork, the fork semantics said that when you do a fork, you have to create a copy of the whole process to a new one, right? So if you do a fork, you're required to make an exact copy of the whole process, right? And that means if you have a large process, you'll have to make exact copy of the whole thing. But turns out most of the forks lead to an exec, right? Which means that you're going to run a new program. In which case, all the things that you cloned are not going to be useful at all, right? So the semantics say that when you do a fork, you have to make a copy of all the pages into a new page. But the reality is, you're not going to use the new ones most of the time. So you're going to fork, and then you're going to discard everything. You're going to proceed, right? So one of the optimization that was done when you have the virtual memory is this notion of copy and write. Essentially, what you do is you need hardware support to implement this. So on the page table, right, before you have valid, invalid bits, right, now if the hardware supports the notion of a read and write, right, so let's say it has the notion of read and write. What this means is, and this is invalid, right, what this means is this page, the operating system says it should only be read only. If you violate that, if you try to write into this at the hardware level, then you get a page fault. If you try to access this, you get a page fault, right? So it's invalid. Whether you try to read or write, you get a page fault. But here, if you read, you're fine. But if you do a write, you get a page fault, right? And this one, you can do a write, so on and so forth, right? So depending on the hardware, you can actually do read, write, execute, right? But for now, we just need read and write, right? So the idea here is when you do a fork, right, I need to create a new page, new process, right? Which means I need to create a new page table. So what I do is I create a new page table. I go ahead, whatever is invalid can remain invalid. Whatever used to be right, I make all of them read. Right? Then I can actually make them point to the same frame. Right? So you have two processes. In the page table, you point to the same frame, right? Logically, you wanted them to be separate. Logically, you wanted them to be two different copies. But you basically make them point to the same page. And through the page table, you mark them as read only, right? So as long as these two processes read this memory, they're fine, right? Even though you're accessing the same frame, it's okay, right? If one or the other process writes, you get a page fault because it's read only, and you try to write. At that time, you create two copies, and you point this to here and this to here, and then modify this to write and modify this to write. Does that make sense? This makes a lot of difference when you do a fork, right? When you do a fork, logically you're supposed to create two processes, each with its own copy of all the data, right? But if you don't actually do anything, if you don't actually write into anything, this optimization means that essentially all I do is I create another page table. They all point to the same frame. So I'm very good with memory management, right? I'm not reusing it, right? And I don't actually, and also creating a fork is much easier, right? Because I don't have to create another page. I don't have to find another frame for this. I can create another process which gets to use all the frames that was available before. But while after I'm running it, as I begin to modify these things, I get a page fault, right? So what do you think of this approach? When will this work, and when will this be a bad idea? This copy and write business, what are the conditions under which it will be a good thing? Yeah? I'm sorry? Yeah. Ideally, if you don't write into anything at all, right, you won't notice a difference at all, right? Yeah, so if you never write into anything, you are good, right? The more you write, the more you pay the cost. The worst case would be if you write into every page, right? In which case, rather than doing it all at once, you're going to do it spread over the time, right? But even then, the overhead may be higher, but you kind of spread out over the long duration, right? So this is one optimization which is possible because of the way virtual memory works, right? Because now you're going to have this invalid bits anyway, right? So if the hardware supports this read and write, now you can also do this optimization such that now you get rid of a whole. So fork now becomes a lot trivial, right? So to create a new process, it's not as complicated as creating a new page. You just create a, you just point to the stuff, right? There's also another cost which I didn't talk about. If you do want to make a copy, right, you have to do memory copy, right? You have to copy all this data to here, right? There's a cost of bringing stuff from hard disk and stuff, but there's a cost of copying all this data from here to here, right? So if you assume that memory read takes 1 clock cycle, and if the page is like say 8K, right, it's not going to be negligible. I mean, there's going to be some cost of copying this stuff, right? So within the operating system, you want to avoid as much copying as possible. We'll see as we move along why you want to do that, and the situation why this happens, right? You would like things to be in one place. You don't want to be copying back and forth within memory because those things still take too much time, right? And this becomes more obvious when you do to the file system. You want to avoid as much copying as possible because the copying, even though it's faster than reading from a disk, it's still you still pay the cost, right? So with the cow model, for the most of the normal processes, it'll work great, right? And it's made possible because you're already doing this through the virtual memory system. And some of the pages which are allocated are zeroed out to 0, right? So this is another operation which may or may not, depending on how you do that, right? If the hardware supports the notion of not zeroing it out, but when you read it, you only get a 0, that's good, right? If you want to give a new page to you, right, the question is, should it be all zeroed out or should it have the old value, right? So one optimization you can do here is to give a page, if the hardware allows it. Whenever you read it, do it, you will only get a 0 till you start to modify it, right? So that way you don't actually write zeros. It only gives you 0 if you try to modify that, read that page, right? And again, the cost is if you want to write zeros to a page, you have to go through and write zeros for the entire frame, which may be expensive, right? You do all this optimization. So if you have like a large matrix in your program, when you allocate the matrix, you expect the values to be 0, right? But you may not actually want to actually write zeros into it. You may let the hardware make it look like it's 0 till you write something in, right? So then it comes down to the notion of a page replacement policy, right? So the policy here is I want some frame for moving my stuff, right? So one process needs a new frame to be brought in, right? And what's the page replacement policy, right? So one of the things you need to worry about is when you do a page replacement, it's a global decision, right? So far we never talked about what it means for the whole system because all the things we talked about, process creation and everything, tended to be per process kind of thing. But the idea here is if you have two processes and let's say that process tries to load something and if it gets a page fault there, right? You have to find some page to bring from here. You got to find some place to replace the frame here, right? But this is being shared by these two processes, not directly but indirectly, right? The amount of physical memory you have is constant, right? So the real challenge is how do you make sure that that one and this one gets the right amount of memory, right? Because that is important because these are two different ones. So if you try to optimize just for that one, if you try to do it based on what the process wants, then you may affect this one, right? So you really want a global policy, right? Can you think of cases why the global policy may not matter, right? So let's think of one policy, right? Let's say you have 100 frames, right? The physical memory has 100 frames. And you have 10 processes, right? Can you just give each of them 10 each? Each process 10 frames? Would that be a good thing? They all get a fair share, right? They all, I mean, there's 100 frames, the 10 processes, so I give all of them 10 frames, right? Yeah.
A couple of them might only use like 2 frames, and some might want like 20, so not very efficient.
Yeah, you're not going to be efficient, right? So if you do it on a global basis, then some processes may not need any frames, very few frames, and some of them may want lots of frames. So you don't want to have this strict policy, right? You want to have these policies of how to manage these things, right? So what happens if you have another process come in, right? Suppose an 11th process comes in, right? Who should it steal the memory from? Right? It's basically to steal memory because it's allocated to other ones, right? It has to start to steal from somebody, right? So the challenge is to figure out how it will do that. So when a new process comes in, who it steals from, and that's one of the magic areas where the different operating systems make a big difference, right? Depending on how they do it, your Vista or Windows may actually turn out to be an excellent thing, or may turn out to be awful, right? Because the penalties, so your program will still work regardless of how we do this, right? Even if the operating system screwed up and then did some poor allocation, your program will still work fine. It's just that it'll be much slower. If it has to go to the disk all the time, it'll be much slower. So that's the challenge. How do you make this global decision such that you still get a good performance, right? And it'll be really good to know that there are some applications which are very important, right? For example, at this time, PowerPoint is the application I'm looking at, right? Because that's all I'm seeing on the screen. So if you can kind of figure that out and then give more pages to PowerPoint, then I may actually be very happy, right? Even though it may be unfair, even though all the frames may be allocated to PowerPoint, I may still be happy. So that's what they tried to juggle around, right? So the basic policy is, you find a free frame. You go through the list to find a free frame, and if you don't find a free frame, you have to figure out something to replace, and then you send it to the hard disk for that particular process, right? The worst case would be if I decide that this frame has to go to the hard disk, and I move it to the hard disk, and then immediately some process wants that, right? In which case it has to be brought in. But in general case, if I can kind of make a good guess, right, then I should be fine, right? So essentially, I have to find a victim page. I have to go through if I don't have a free frame, I have to find a victim page. I have to swap it out and then swap things back in, right? And one of the things you can do is, if this was never modified, which is sort of what you're doing for the homework project too, right? If this was never modified, you don't have to do this the first step, right? If a page was never modified, that means you expect whatever was in the swap to be valid, right? So only if a page was modified, it has to be returned to the hard disk because you want to save the contents, right? So you may have a policy which prefers pages which are not modified over pages which were modified. Because if a page was not modified, you only pay the cost of bringing a new page in. If a page was modified, you have to pay the cost of moving a page off and then moving a page back in, right? And you also have to have data structures which state that, which lock that page, right? Essentially what happens is, if the operating system decides that that page has to go to hard disk, it doesn't usually sit there and wait for the things to finish, right? So it'll lock it and then basically start the process of writing to the hard disk. When the hard disk finishes, then it'll start the read one and bring it back in, right? While it's doing all this stuff, you don't want another thread to come back and say, oh, I see a victim page, I'm going to use it, right? Till this whole process finishes, you don't want it to be allocated to anything else. And so it may take you a while to do this stuff, right? And so some of the cases that you'll see in a real system is, suppose you decide that's a victim page, right? That you're trying to evict to a hard disk. What happens if another thread from another process touches that page? What do you think should happen? Right? Another process, that page belongs to another process, right? And that process now accesses that particular page. But you already started the process of writing it to the hard disk, right? What do you think should happen? What would you do? Again, there's no right or wrong answer. It depends on what the operating system wants to do, right? What would you do? Do you go through step 1, step 2, and then find, read that back from here to another page separately, or about this process find another page, even though you return, right? Even though you went through step 1, Step 1 is not catastrophic. It just basically means that it's returned to the hard disk. That means in the future it can be used, right? So do you kind of abort it and then find another page for this victim? Which one would you prefer? Or it doesn't matter? So the answer is it depends on what they find, what they try to see, right? It depends on how often this happens, right? So if it happens often, they may be able to short circuit it. If it doesn't happen often, they don't really care about it, right? The challenge here is the more it has to do all this complicated stuff, the operating system becomes more and more complicated, right? You want all this stuff to happen really, really fast because you get a page fault. I want all this to be done really quickly. I don't want to do all this corner cases. I don't want to see, okay, what if this happens, what if this happens kind of stuff, right? So sometimes operating systems may be dumb, but they may just go through all the steps just because that is what they wrote, right? Unless there's really proof that this is causing some trouble, then you use tools like PIN or something to figure out what is happening. Then you may try to optimize this stuff, right? In general, operating systems people don't want to optimize. They don't want to make stuff more complicated, right? Because this has to run really, really fast. You're not trying to make them as complicated as possible. You want this darn thing to work, right? So in general, it's very conservative. They don't try to just modify something because, unless there's like all the things I'm talking about, right? There's one case where it may be fine. There's another case where this may be horrible. Unless you have really proof that it's horrible, don't mess with it, right? And that's one thing you have to remember throughout the system, right? You're not trying to find the most optimal solution. We're not trying to find the best solution. We're not trying to find all this stuff. You want something which works reasonably and keeps going. You want to tweak it a little bit, but not really drastically find nice data structures. So if you I'm not sure how many of you have taken a data structures course, right? So if you took a data structures course, you may talk about skip lists and all those things, right? More complicated data structures which will make the things go faster. You don't traditionally tend to do that. You do a linear search or what have you, because you want the system to be easy to manage, easy to look at. Unless there's proof, you don't try to do those things, right? So one thing you can do is you can look at the page fault traces, and then you can think of different page replacement policies and kind of guess how much page faults you will get, right? And this simulations you sort of do it, and this is part of what you're doing for your homework project, right? Essentially, you want to get a sense of how much page fault you'll get for a given policy, right? In real systems, it becomes more complicated because there are other processes and other threads. But this is a simple way to kind of get a sense of what happens, right? So, for example, let's assume that you have this page trace like 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5, right? And in your case, the number will be a lot bigger because it's a 64-bit number. So this will be a really big number, really big number, and so on. But essentially the same concept, right? And what you would sort of like is, if I give more pages to you, I would like your page faults to come down, right? That's sort of what I would want. If I buy more memory, if I give more memory to your process, I would sort of want your page faults to come down. Because page fault means that something has to be brought in from the hard disk, read or write, which is we want to avoid. So you sort of want this kind of a graph, right? So that's what you're trying to draw. So when you do the simulations, you're trying to figure out, if I give more frames, does the page fault keep going down? And ideally, at some point, you like the page faults to go to 0, in which case you're running happily, right? And in your case, you're trying to see if you allocate the number of frames that you really need for your program, right? You're trying to look at number of frames, quarter, half, and all those things. But when you have the number of frames that you want for your program, you only get the page fault the first time and nowhere else, because you have enough memory to run your program, right? And so even though this may look obvious, there are conditions where this doesn't happen, and we'll see why in a little bit, right? So the first algorithm we're going to look at is first in, first out, right? So the reference string that you have is 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. Essentially for your project, you generate that with pin. The pin tool gave you that address. Of course, it's a big number, but essentially you have those stuff. Then you figure out how much frames you have, right? So if you have first in, first out, which is a simple enough policy, right? You basically, so you start off by 1, 2, and 3, right? So I have 3 frames, right? So you first request 1, then you put it here, then you request 2, you put it here, then you request 3, I put it here, right? So now you request 4, right? I'm doing first in, first out. So this is the first one to in. So I want to replace this and put 4, right? And then I want to access 1, which would have been good if I was a little smarter, but I wasn't. So the first one in was this, so I had to move this, and then I do this, right? And then 5, right? And I replace this with 5, and I do 1, 2, 3, 4, 5. So 1 was already there, so I'm good. 2 already here. Now I want to replace 3, and so I replace this with 3, and then I want 4. I replace this with 4, and 5 is already here, right? Does that make sense? Right? So first in, first out basically looks at the pages, and whichever was the first in is thrown out. And as you can see here, if I was a little smarter, I could have avoided some of those stuff, right? So here I replaced 1, and then the next instruction was 1. So if I had known the future, I would have been happy, but since I can't, I have to go through the stuff. So essentially that gives me a trace of how many page faults I'm going to see. And you can do the same thing for if you have 4 frames and so on and so forth, right? And if you went through the stuff, the 9 page faults when you had 3 frames. When you had 4 frames, you actually get 10 page faults, right? So the nice graph we thought we should get, it's not really true. And this is called Ballard's anomaly, right? Where you have more memory actually makes your program behave worse, right? I have more memory. So if I plot the number of frames and the number of page faults, I get these cases where when I have 4, the page fault actually goes up, right? So compared to 3, right, I have more memory, but I have more page faults, right? So that's one of the reasons why you want to look at this stuff, right? You want to try to figure out what's the number of page faults you're going to get for different policies, right? And again, like we said before, we're not trying to look for very complicated algorithms. We're trying to look for simple algorithms, easy to implement and faster and stuff. And you want to draw some graphs like this to see how many page faults you get, right? And operating system folks do a lot of these things. They use tools like pin to get the traces, right? So the idea here is if you assume that most of the Windows machines are going to run PowerPoint, I generate the access trace for PowerPoint, and I see how much page faults you got, and I try to tweak the algorithm, see if the page fault rate goes down, right? Then you're going to see a massive performance improvement, right? So before you do all this stuff, you want to look at what's the optimal policy, right? Because then you can see how much you can improve. So you want to tweak it. So you want to get a bound of what is optimal policy, right? And what do you think is the optimal policy? So we kind of looked at it from the previous case, right? So when we were looking at the page 1 was going to be used pretty much in the future, right? So optimal policy turns out is a policy where you replace the page which is not going to be used for the longest time into the future, right? So in the case of you looking at the case, so 1 is going to be used in the near future. So if I can look at the reference string, if I know what is going to be used in the future, the one which is going to be used the longest in the future should be the one which should be replaced, right? Not the shortest one, right? So that's the optimal policy, right? Can we implement the optimal policy? Can you know when a page will be used in the future? You can't, right? Because when a program runs, the program does not tell the operating system what it's going to do, right? We can try to be smart, we can try to predict based on what you've done so far, but we can never know what the future is, right? So you can never achieve the optimal policy, but hopefully we can come close to it, and that's what we try to do in some of the more smart algorithms, right? So in the next lecture, we'll continue with looking at the different policies, but essentially you're trying to see, this is the most optimal policy, we can't implement this, what can we do in the hardware, what can we do such that we can achieve close to that without knowing what the future is, and that's the focus of next lecture, right? And I'll see you guys on next Wednesday, right?